Hey everyone, in this video I'm going to go over Module 3, Protocols and Models. Just keep in mind I am in an instructor view here, and so yours might look slightly different on the NetAcad site. So in this chapter, we learn about why protocols or rules are important in networking. This is a rather large chapter, and it sort of lays the foundation for the rest of the course because the rest of the course follows the OSI model, which is a topic which I'll get into here a little bit in this video. So a wide variety of topics here. I'm going to try to briefly go through these. Again, I would highly recommend that you read through these on your own. So first, the rules or communication protocols. So protocols, think of rules. When we communicate as humans, we don't necessarily have formal rules all the time, but we do some things that are in common for everything that we transmit, so to speak. So we always have a source who is talking, and we always have a destination who is listening. That source typically is one person. That destination is typically another person, but it could be a group of people as well. So keep that in mind. Or it could be a specific subset of people. Like maybe you're in a room and you're just talking to one table. If there's a bunch of tables in the room. That kind of relates to our unicast, broadcast, and multicast traffic, as we'll learn later on in this course. But when humans communicate, like I said before, we don't necessarily have a lot of formal communication. We may do some things like nodding or smiling to, let the sender know that, hey, we heard you. Hey, we got your message. We might shake our head if we don't agree, or we might say what or pardon me if we need someone to repeat something. But with computer networks, we can't rely on that informal communication protocols or rules. We have to have everything structured. We have to know how long we're going to send. We have to know if we're going to give acknowledgement of receipt. We have to have all of these things laid out. Otherwise, network communication would just kind of be a disaster because we wouldn't have anything consistent. So that's what this first section is trying to really explain is that we need some sort of rule establishment with our computer networks. Otherwise, communication on a computer network just really isn't going to work. So some of the things that the protocol or rules establish is how we're going to encode the message, the formatting and encapsulation, the size, the timing, and our delivery options. I'm going to scroll down here to this analogy. I love this analogy because it's exactly what a computer network does. So if you're going to send a letter to a friend, you need to put that letter inside of an envelope. You need to put an address on there, actually a couple of addresses. You put who the sender is. So up on the upper left-hand corner, you put who the sender is. That's you typically. And you put who the recipient is. On that address, we have a bunch of things that makes it unique. We have the city, the state, the zip, we have the street, we have the number, and we have the sender. There could be a bunch of 100 main streets throughout the world, but there's probably only one 100 Main Street, Bismarck, North Dakota 58501. So all of those things make it unique. Just like a computer network, we need to keep things unique. There could be, hundreds, millions, billions of computers in the world, hundreds, millions, billions of cell phones. How do we deliver that internet traffic, that network traffic to the correct cell phone, to the correct computer? The address helps us do that. There's a few different addresses we'll learn about in this class. There is the layer 3 address or the IP address. And there's also a layer 2 or MAC address. Those addresses are used to pinpoint the exact device that was the sender and the exact device that should be the receiver. Another thing that we do with our message is we change the size. So going back to that letter example, what we would do, whoops, I scrolled down, I didn't want to. What we would do here is if we had a, say, 50-page letter, when humans are communicating, we'd put it in one envelope, a larger envelope, we'd put a little extra postage on it, and we would send it. Well, what computer networks do is they take each individual page, they put it in an individual envelope, and then they send it. So we are always breaking up our messages into smaller, more manageable chunks. We do something called encapsulation, and what encapsulation means is adding all that address information. So it may seem highly inefficient to you to take a 50-page letter and put it into 50 different envelopes, but for computer networks, it's actually more efficient because then we can track whether or not the chunks made it. We can put them in the correct order. If just one piece of the letter went missing, we can request just for one piece of the letter without having to resend it. So if you're going to download, let's say, I don't know, a movie file maybe 4 or 5 gigabytes, for example. If you're trying to download that in one big chunk and it had one error, you'd have to start all over. And so you'd constantly be trying to restart this 5 gigabyte chunk over and over and over. Whereas if we divide it up into smaller parts, typically it's about 1,500 bytes in an Ethernet frame. If one Ethernet frame goes missing or gets corrupted or has an error, all we have to do is send that one Ethernet frame, not the whole big 5 gigabyte file. Our protocols also dictate our timing. I guess I'll use this example. If you've ever downloaded something, you may have noticed that the speed fluctuates as you download. That's all having to do with the timing. At one point in time, the receiver might say, "Hey, slow down. I can't accept quite as much information," and then the sender can speed up. Um, or it might say, "Hey, I can accept more information, so you can send more information at a time, more bytes at a time." So in this little example here, it's just talking about the message timing, and they're kind of talking at the same time, and they collide, and that can actually happen on a computer network too, where two computers talk at the same time and cause a collision and some interference. It doesn't happen with our modern day networks, but the reason why it doesn't happen is because we have all of these rules and protocols in place so that it doesn't. It will also define our message delivery options. I mentioned this already. Unicast is one-to-one. So one person talking to another person, one computer talking to another computer, one cell phone talking to a server, so a one-to-one. Multicast is one to many, but not one to all, but one to many. So the example I like to use is, you're in a room with several tables, maybe round tables, and you're the speaker and you go over to one round table and you start communicating with just that one table. That's multicast. While there's other people in the room, they're not hearing that message because you're just talking to the one table. And then a broadcast is one to many or one to all. So in this case, she's talking to everybody in the room, and computers do that as well. Some examples of broadcast traffic is DHCP. DHCP traffic is when your computer gets an IP address. We'll learn more about IP addresses later, but an IP address is required to be unique and on the network, so you can have traffic delivered to it. When you ask for an IP address to get put on a network, that is a broadcast message. So you essentially yell out on the network, or you yell to everybody, "Hey, is there anybody out there that can give me an IP address?" And I'm, making this example up, but that's essentially how it works. And then a DHCP server hears it and sends a message back and says, "Hey, I am a DHCP server. I can give you an address. Here's the address." The computer accepts the address, thanks the server for it, and then the server acknowledges the receipt of that address. The next part is all about protocols. So protocols define all of the things I just talked about. The timing, the message delivery, is it going to be unicast, broadcast? How big can the message be? All those sorts of things. Well, there's several different types of protocols in computer networking, and it's just much too large to get into right now. So what I'm going to talk about is TCP/IP. TCP/IP is the main protocol that we have on our computer networks, because TCP/IP is the protocol that is required to be on the internet. There are other protocols out there, such as, and these are old, but AppleTalk and SPX, XPX. There's also proprietary protocols out there, but pretty much every computer, every device that can access the internet or has a web browser runs TCP/IP. I shouldn't say pretty much, they all do, otherwise they can't be out on the internet. So that is the main protocol that we will focus on in this class. And within the TCP/IP protocol, there are a bunch of sub-protocols. So for example, when we go and we surf the web, that uses HTTP, Hypertext Transfer Protocol. That is a subset of the TCP/IP protocol. I just mentioned DHCP. DHCP is under the umbrella of TCP/IP. That's how you go and get the IP address. DNS, that resolves host names to numbers. So like Cisco.com, what is its IP address? We'll get into all these different things as the class goes and continues. That's why this chapter is very foundational. Highly recommend that you read it. So again, the main protocol is TCP/IP. Again, that defines all of the rules behind our communication. That's very, very important in our computer networks because we have to have everything defined and be specific. And then underneath that, we have a bunch of sub-protocols. So this next section gets into that protocol suite, the TCP/IP, and it talks about some of the different sub-protocols that are in there. How does Ethernet work? That's our wired communication. How does HTTP work? Some other things that are in there, I already mentioned DNS and DHCP, but there's SMTP, that's mail delivery. Same with POP3 and IMAP. There's file transfer, FTP. There's also SFTP, which is the secure version of that. We have HTTP, HTTPS, and you can see all of these different sort of sub-protocols of TCP/IP here. And all of these make up how we communicate on our modern networks and how we access the internet and how we use the internet and how we get web pages and how we stream video and all those sorts of things. I will go and say this, that there's probably an individual chapter for a lot of these different protocols. Not like a chapter dedicated just to that protocol, but in a particular chapter, it will talk about these protocols in more depth. So for example, the application layer chapter, I don't remember what chapter is the application layer. I think it's like chapter 13 or something. It gets more into SMTP and POP and FTP and HTTP. When we get into the network chapter, I think it's like chapter 5 or something, it gets more into DHCP and DNS. So more of this to come, but just note TCP/IP is our main protocol suite. Again, the protocols define how our communication is going to work. And then under TCP/IP, we have some of these other kind of sub protocols that adhere to how TCP/IP works. Now, where the heck do these protocols come from? These protocols come from different standards organizations. So there are some open standards, and open standards means that anybody can use the protocol or standard. Some of those standards come from IEEE, IANA, ICANN, TIA. I'll just give you a couple examples. Wireless communication. How far can the wireless signal go? How fast can that wireless signal go? What kind of antenna can you have? How many antenna? All of that is the IEEE 802.11 standard. So if you wanted to get real nerdy and read about how Wi-Fi works, you can go look up the IEEE 802.11 standard. And the latest as of this video is the 802.11ax standard. It's the latest and greatest, can go the fastest. It has more channels, all of those different things. They're defined by the IEEE. If you have a wired internet connection, or your computer has a wired connection, how that connector looks, how it's pinned out, what the shape and size and the dimension of that connector, that's the TIA 568A standard. IP addresses and where they come from, that's either under the IANA or the ICANN standards. So that's where they come from. Is it important that we know where they come from? Probably not so much, but just so you know that it's not, some guy developed it on his own. These people get together, they create the standard, they open it up, that's why it's called open, for other people to look at it, to make comments, and then in the end, what they do is they ratify it, or basically, kind of put the stamp of approval on it, and then people can start using it. Now, if you're, say, Microsoft or Apple or any organization, you can create your own standards. So for example, Apple had like the Lightning connector for a long time. That was their own standard of how that looked and how that worked. But what we found out and through some legislation is it wasn't very universal, so they went to USB-C. And we like open standards. That way anyone can use them, and we can ensure some interoperability between our different manufacturers. So that's what this section's all about. Who are some of those different standards organizations? Where do they come from? Reference models. Reference models give us an idea of how communication works on the network. What I am going to refer you to here is this OSI layer model video. I think it will really give you an idea of how the OSI model, TCP/IP, not in a ton of detail, but how that really works in our network communication. In this PowerPoint video, I run through how an email gets sent from a computer in America over to a computer in Australia. Like, not a ton of like the gory details, but just an idea of how we break down that email into smaller chunks, how we add the addresses, and how we get it to the email overseas. Another video I would draw your attention to would be Warriors of the Net. It's old video, but it actually does a very good job. So Warriors of the Net gets into how network communication works. It shows how encapsulation works, how routers work, switches. Again, I highly advocate that you guys watch it. Please do so. It gives you a very good understanding of how network communication works. The other model that's out there is the TCP/IP model. We don't spend a whole lot of time on the TCP/IP model because if you look at the TCP/IP model, it matches up very similarly with the OSI model, and the OSI model gives us a little bit better breakdown. It's a little bit more fine-grained, so that gives us a better understanding. So going forward in this class, we're going to have individual chapters on each one of these layers. You might be thinking, well, why so many different individual chapters? Why so many different layers? It makes it easy. So down at the physical layer, all you worry about is the physical connections. What do the cables look like? How long can they be? What do the connectors look like? We don't have to worry about the web browser. We don't have to worry about the routers, all of that stuff. We just worry about the physical connections. Up here at the network layer, that's where the routers work. So we worry about routers and IP addresses. Up at the application layer, all we care about is the applications that use internet. So our web browsers, our email applications. We don't care about the physical connection. That's down here in layer 1. We don't care about the routers and the IP addresses. We just care about the application. So breaking down network communication into these smaller, more manageable chunks really helps us understand and define how networking works. The next section is about data encapsulation. Just think about data encapsulation as breaking down that message into smaller chunks and then putting the things we need on those chunks to ensure delivery. Well, what types of things do we need to add? IP addresses, MAC addresses, the type of communication it is, such as DHCP or DNS and all those different things. So right here, this computer is sending messages and it's breaking it down into smaller chunks. That's what this data encapsulation is all about. We put them in the right order by putting sequence numbers on them. We take a look and put the data into certain forms depending on where we are at in the OSI model. In the end, we get to bits, ones and zeros. So that's what this section talks about, is breaking down that communication into smaller chunks and then adding all of the different things we need on that data chunk, I should say, to get it down to its or get it to its destination. That's what this Warriors of the Net video really does a good job at, is showing you how that works. So again, I highly recommend that you take the time to watch it. Data access section here. This is kind of our first glimpse into addressing or IP addresses. So I'm going to just show you a couple things here. If you go out to the command prompt of your computer and you type in ipconfig, ipconfig shows you what the IP address is of your computer. Now I have something called VMware installed. We don't care about those adapters. I'm worried about either my wireless, because I'm wireless, or if you're wired up, you would look at your Ethernet adapter. So I'm wireless right now, and my IP address is 192.168.1.44. What I want you to know right now is that there are no two IP addresses that are the same in the world. There cannot be another computer that has 192.168.1.44. Why? Because if, for example, Google is trying to give a search result back to the computer at 192.168.1.44 and there's 50 of them, how does Google know whether to deliver that search result to my computer or the other person's computer with that same address or the other person's computer with that same address? So all IP addresses have to be unique in the world. There's a little asterisk to that. We'll talk about that later. But for right now, I want you guys to know that every single IP address is unique to every device. So every device that's on the internet has to have a unique IP address. There's another address. If we do an ipconfig/all, all gives us more detailed information. That other address is the physical address. The physical address is also known as the MAC address. Now, what this shows is a burned in address, as it's called, a number that is unique to that network card and that network card only. It's a little bit different than the IP address because what we'll learn with the IP address is that with the IP address, we can determine what network we're on because we have something here called the subnet mask. But with a physical address or a MAC address, we cannot. I'm going to go back to the IP address here real quick. So I see 192.168.1.44, and then I see 222.5.5.0. What this tells me is my computer is on the 192.168.1 network, and I'm the 44th computer on that network. The 192.168 and 1 match up with the 255s, and the 44 matches up with the 0. Again, what that tells me, and we'll get to this, is that I'm on the 192.168.1 network. Now, with this physical address, I don't have that. Instead, I have the first 6 hexadecimal digits. That tells me the make and model. So if you also had an Intel Wi-Fi 6E AX211 card, your first 6 are more than likely going to be F4C8A. And then the last 6 are just randomly generated. It's kind of like the serial number, so to speak, of that network card. So going back to chapter 3, this data access talks about those addresses. The source IP is where it came from. The destination IP address is where it's going to. And again, right now I want you guys to know that these addresses are unique. There is no two computers that have 192.168.1.110 and 172.16.1.99 in the world. They're unique to this web server and to this PC. If we're on the same network, we take one step back. If we're on remote networks, the only way we can communicate with remote networks is IP addresses. But if we're on the same network, we can communicate using the MAC address. So all of these A's represent the MAC address. All of these C's represent the MAC addresses. But as I just mentioned, you cannot use the MAC address to communicate outside of the network. So I highly recommend that you guys, again, read this chapter, take a look at that Warriors of the Net video, take a look at the OSI model. I know that's a lot of time, but this chapter, again, sort of lays the foundation for everything to come. It's only going to make things easier for you. So just talking about the role of how those different addresses work, MAC addresses, IP addresses, source, destination, all of that sort of stuff. Here we have to install Wireshark, so you may want to make sure that you get Wireshark downloaded and installed. What Wireshark does for us is it allows us to sniff network traffic. So what I can do here, and this video is not meant to give you a how-to into Wireshark, so I'm just going to quickly start it up. I'm using my Wi-Fi and I can see traffic going through it. As I start to sniff network traffic, I can start to see all the different packets and frames coming through. Now, this is a tool that hackers use because they can look inside of a packet and actually view the raw data that's being transmitted on the network. Now, if my network traffic was not encrypted, I could view this in plain text. So, for example, can I find one? If I did DNS, I probably could. Let me just do a few. Oops, I already did ESPN. Okay, so if I flip back here, let's see if I can find a DNS packet. So I can see my different protocols. Here's DNS. Whoops, I clicked. So in this DNS packet, we're asking what is the IP address of assets.msn.com. So if you're a network administrator and you want to get an idea of where people are going on the network, you could start to see URLs, assets.msn.com-world-atm. I should actually use my filter here. This will show me all DNS traffic. All right, so www.youtube, what is its IP address? Google.com, all those different places that I went, ESPN, I can start to see all the different places that people went. And this traffic is not encrypted, so I can see it in plain text. I can see the different websites that people are going to. So if you get a chance, mess around with Wireshark. We'll be doing a lab with it actually. So get it installed, check it out. I think that about does it for this video. Again, I went through it briefly and here I'm at 27 minutes, so I apologize for the length. But you're going to want to read through this. You're also going to want to watch Warriors of the Net and then also watch this OSI model video. That's all. Thanks for watching.